Chapter Radiation MCQ number 4. If the absolute temperature of a body is doubled, the power radiated will increase by a factor of. Your options are option A 2, option B 4, option C 8 and option D 16. Students, using Stephen Boltzmann law of radiation, we can say like this: the power radiated by a body is directly proportional to the fourth power of its absolute temperature. In this MCQ students, it is given that हम temperature को double कर रहे हैं. So can't I say like this: the power radiated will become 2 raised to 4, that is 16 times. And that's why the correct answer is option D 16. Chapter Radiation MCQ number 5. Calculate the value of lambda max for radiation from a body having surface temperature 3000 Kelvin. It is given that B is equals to 2.897 into 10 raised to minus 3 meter Kelvin. Your options are option A 9935 Armstrong, option B 9656 Armstrong, option C 9421 Armstrong and option D 9178 Armstrong. Students, over here we can use Wien's displacement law. As per this law, lambda max is inversely proportional to absolute temperature. That means lambda max is equals to B divided by T. यहाँ पर स्टूडेंट्स B का मतलब होता है Wien's constant. Its value is also provided to us. B is equals to 2.897 into 10 raised to minus 3 meter Kelvin. That means students, हम कह सकते हैं lambda max is equals to 2.897 into 10 raised to minus 3 meter Kelvin. The whole upon absolute temperature is 3000 Kelvin, or we can say this is 0.3 into 10 raised to 4 Kelvin. Alright, now students, 2.897 divided by 0.3 will give us 9.656. Alright, into we are getting 10 raised to minus 3 minus 4, that is minus 7. That can obviously be considered as 9656. Shifting 3 decimals. So into में हम लिख सकते हैं 10 raised to minus 10. So students, we got lambda max in SI unit. That means this is 9656 into 10 raised to minus 10 meter. That is 9656 Armstrong. And that's why the correct answer is option B 9656 Armstrong. Chapter Radiation MCQ number 7. Calculate the energy radiated in 1 minute by a black body of surface area 200 centimeters square at 127 degrees Celsius. Value of sigma is provided 5.7 into 10 raised to minus 8 joule per meter square per second per Kelvin raised to 4. Your options are option A 1367.04 joule, option B 1698.04 joule, Option C 1751.04 joule and option D 1856.04 joule. Students, time is equals to 1 minute, that is 60 seconds, by a black body. That means its coefficient of emission is equals to 1, small e is equals to 1. Its surface area A is 200 centimeter square, that is 200 into 10 raised to minus 4 meter square. Its temperature capital T is 127 degrees Celsius, that is 127 plus 273, that is equals to 400 Kelvin. The value of Stephen's constant sigma is given as 5.7 into 10 raised to minus 8 joule per meter square per second per Kelvin raised to 4. Over here we have to find out the energy radiated by the black body. That means Q is equals to how much? Students, using the formula that we got from Stephen Boltzmann law of radiation, we say Q by T is equals to E A sigma T raised to 4. So the required value of Q can be taken as T into E A sigma T raised to 4. That means students, we get Q, that is heat radiated, is equals to time, which is 60 seconds, into small e emissivity is equals to 1 into surface area of the body 200 into 10 raised to minus 4 meter square into sigma Stephen's constant 5.7 into 10 raised to minus 8 in SI units into T raised to 4, that means 400 the whole raised to 4. That is students, Q is equals to 60 into 200 into 5.7 into 10 raised to minus 4 into 10 raised to minus 8 into 4 raised to 4 will give us 256 into students 10 raised to 2 raised to 4 will give you 10 raised to 8, isn't it? Now students, 10 raised to minus 8 and 10 raised to plus 8 will be cancelled. So we will get Q is equals to 1751.04 joule. So this is the required energy radiated by the given black body. Q is equals to 1751.04 joule, and that's why the correct answer is option C, 1751.04 joule. Chapter Radiation. Short answer 1. Question number 6. Compare the rate of radiation of metal body at 727 degrees Celsius and 227 degrees Celsius. Temperature for first case of the body, let's say T1, is given as 727 degrees Celsius, that is 727 plus 273, that is 1000 Kelvin. Second temperature of the same body, let's say T2, is equals to 227 degrees Celsius, that is 227 plus 273, that is 500 Kelvin. We have to compare the rate of radiation, that is, we have to find out the ratio of rate of radiation, that is R1 divided by R2 is how much? The formula for rate of radiation can be taken as dq by dt is equals to EA sigma T raised to 4. Let's say this dq by dt is denoted by capital R. Using this same formula for two different temperatures, we get R1 is equals to EA sigma T1 raised to 4, and then R2 is equals to EA sigma T2 raised to 4. So the required ratio R1 divided by R2 is equals to EA sigma T1 raised to 4 the whole upon EA sigma T2 raised to 4. Now students, coefficient of emission E gets cancelled, surface area gets cancelled, Stephen's constant sigma also gets cancelled. So we are getting R1 divided by R2 is equals to T1 divided by T2 the whole raised to 4, that is 1000 divided by 500 the whole raised to 4, that is 2 raised to 4, that is 16, or we can say 16 is to 1. So the required ratio of rate of radiation, that is R1 divided by R2, that is dq by dt for first case divided by dq by dt for second case is equals to 16 is to 1. Chapter Radiation, short answer 1, question number 7. 1000 calories of radiant heat is incident on a body. If the body absorbs 400 calories of heat, find the coefficient of emission of the body. Total 1000 calories of radiant heat is incident on the body. That means Q is equals to 1000 calories. If the body absorbs 400 calories of heat, that is QA, quantity of radiant heat which is absorbed by the body is equals to 400 calories. We have to find out the coefficient of emission of the body, that is small e is equals to question mark. First of all students, we can find out the coefficient of absorption of the body, which is also called as absorptivity, which is denoted by small a. The formula of small a is QA divided by Q. So we get A is equals to, the value of QA is 400 calorie divided by Q, which is 1000 calorie. So 0 gets cancelled. We are getting students 4 divided by 10, or you call it as 0.4. So students, the value of coefficient of absorption is 0.4. Now students, as per Kirchhoff's law of radiation, at a given temperature, the coefficient of absorption of a body has to be equals to the coefficient of emission of the same body, that is equals to 0.4 as per the given data. So the required value of coefficient of emission of the given body is 0.4. Chapter Radiation, short answer 1, question number 8. A metal cube of length 4 cm radiates heat at the rate of 10 joule per second. Find its emissive power at given temperature. So the body is cubical in shape. Its length L is equals to 4 centimeter, or we say this is 4 into 10 raised to minus 2 meter, and it radiates heat at the rate of 10 joule per second. Heat emitted per unit time Q by T is equals to 10 joule per second. We have to find out the emissive power at given temperature. That means capital E is equals to question mark, students. This is a simple numerical based upon the basic formula of emissive power. Let me remind you students, ये जो emissive power होता है इसका और एक नाम होता है radiant power, जिसका फॉर्मूला होगा कैपिटल E is equals to Q divided by AT, which can be taken as Q by T, the whole upon surface area of the body. The body is cubical in shape, so its surface area has to be 6L square. So students, the value of E is equals to Q by T, which is 10 joule per second, divided by 6L square, that is 6 into 4 into 10 raised to minus 2 the whole square, that is 10 divided by 6 into 4 square will give you 16 into 10 raised to minus 4, that will give you 10 raised to 5, the whole upon 96. On simplifying further, we get 1041.666, that is basically recurring. So we can say this is 1041.67, and this is the answer of emissive power. So its SI unit has to be joule per meter square per second. Hence, the required emissive power of the body at a given temperature is equals to 1041.67 joule per meter square per second. Chapter Radiation, short answer to question number 5. Compare the rates of emission of heat by a black body maintained at 627 degrees Celsius and at 127 degrees Celsius. If the black bodies are surrounded by an enclosure at 27 degrees Celsius. As per the data given in this question, first temperature of black body, let's say T1, is equals to 627 degrees Celsius, that is 900 Kelvin, and the next temperature of the same black body, let's say T2, is equals to 127 degrees Celsius, that is 400 Kelvin, and the temperature of the enclosure, or we can consider it as temperature of the surrounding, which is T0, is equals to 27 degrees Celsius, that is 300 Kelvin. We have to compare the rates of emission of heat by that black body. That means we have to find out the ratio of rate of emission in first case, that is R1, divided by rate of emission of heat in second case, that is R2. So we have to find out R1 divided by R2 is how much? Students, the general formula to find out the rate of emission of heat when temperature of surrounding is provided in the data goes like this: Q by T is equals to E A sigma the whole into t raised to 4 minus t naught raised to 4. Let's say students, this ratio of q by t is denoted by capital R. So we can use the same formula twice. For first case, we can find out rate of emission R1, that is EA sigma into T1 raised to 4 minus T naught raised to 4. And for second case, we can find out the rate of emission R2, which is equals to EA sigma into T2 raised to 4 minus T naught raised to 4. So simply we have to find out the ratio of R1 to R2. So we can say like this, R1 divided by R2 is equals to EA sigma into T1 raised to 4 minus T naught raised to 4, the whole upon EA sigma the whole into T2 raised to 4 minus T naught raised to 4. So students, E will be getting cancelled, A will be getting cancelled, sigma will also be getting cancelled, and हमें मिलने वाला है R1 divided by R2 is equals to T1 raised to 4 minus T naught raised to 4, the whole upon T2 raised to 4 minus T naught raised to 4. Substituting the values provided to us, we get R1 divided by R2 is equals to 900 raised to 4 minus 300 raised to 4, the whole upon 400 raised to 4 minus 300 raised to 4. So cancelling 10 raised to 2, the whole raised to 4 from the numerator as well as denominator, we get R1 divided by R2 is equals to 9 raised to 4 minus 3 raised to 4, the whole upon 4 raised to 4 minus 3 raised to 4. That means R1 divided by R2 is equals to 9 raised to 4, that is 6561 minus of 3 raised to 4 will give us 81, the whole upon 4 raised to 4 will give us 256 minus 3 raised to 4 will give us 81. So students, we are getting 6480 divided by 175. That means students, R1 divided by R2 is equals to 6480 divided by 175. That is equals to 37.0286 on rounding off. We are getting 37.03, or we say the required ratio of R1 to R2 is equals to 37.03 divided by 1. So the required ratio of rates of emission of the given black body is equals to 37.03 is to 1.